It's working. Okay, good. The clicker is now working. Great. So the lecture is going to be an hour and a half. Feel free to interrupt me at any time. As I said, I've got lots of slides to go through. And if I don't get through them all, it doesn't matter because it's sort of ordered in increasing, complexity. So it's best to get the stuff early on right. So I'm going to spend about 30 minutes on each of these sections: cosmological history of ultralight dark matter, cosmic structures of ultralight dark matter, and compact structures of ultralight dark matter. If we get time at the end, there's even more stuff we can talk about: intensity mapping and pulsar timing arrays and things like that. I've highlighted in a few places on the slides where there are problems that you can do. The problems are in this article here, which is a chapter in a textbook called Ultralight Bosonic Dark Matter, and there are solutions to the problems as well. So watch out for where I tell you to have a look at the problems. This is some nomenclature. I'll freely use the term ultralight bosonic dark matter, ultralight axions, ultralight dark matter. These are all interchangeable terms for the purposes of this lecture. And I have no idea what units I'm using, and I have no idea what factors of 2 pi are, so don't worry about those. Right, okay, so let's start with production of ultralight dark matter. Production proceeds as a classical field. And the thing that you need to think about with axion-like particles in particular is about symmetries. So the QCD axion is our template model. We'll talk a lot more about the details of the QCD axion tomorrow, but we can think of it as a template overall. It's a pseudo Goldstone boson. So Goldstone boson, something that's massless due to the breaking of a spontaneous global symmetry. Pseudo because it's not exactly massless. So for the QCD axion, we have this complex field, which we call the PQ field, the Pet-Shake-Win field, field phi, and we write it in polar coordinates, rho e to the I theta. The axion is the phase of this complex field. Spontaneous symmetry breaking means we have this wine bottle-like potential here, and the potential looks like this. V is the spontaneous symmetry breaking scale, which is the distance from the maximum in the middle to the punt around the bottom of the wine bottle. And the Goldstone boson, the axion, is the angular direction around here. So when this field gets a vacuum expectation value and spontaneously breaks to global symmetry, there's a field theta that goes around like this, which is the nonlinear realization of that symmetry. So the U1 symmetry tells us that the action is unchanged by a constant complex change of phase to the field phi. And you can just see from the coordinates there that the complex phase of the field phi corresponds to a shift of the angular direction of the axion. So we say that the axion has a shift symmetry, but it's really just a U1 symmetry. It's a global symmetry, which tells us that this alpha factor here is a constant in the phase, so the derivative of alpha has to be 0. Symmetries break at phase transitions. So the universe is hot in the early universe, and there are fluctuations. And when there are fluctuations, the field phi is moving around like this, and it doesn't see the fact that there's a minimum. So on average, it's 0. As the universe cools and the temperature decreases, okay, this is what I've just said. There's fluctuations, and the field doesn't see its minimum. When the temperature drops, such that the fluctuations of the field are smaller than the distance here to the VEV, then the symmetry breaks, and the state of the field, which was that blob, now rolls down, and it can be any of these things here. Theta chooses a direction at every x, and that spontaneously breaks the U1. Spontaneous breaking of a U1, the simple physical picture you can have in your mind is a pencil. You balance a pencil on its end, you wait, and it will fall over. Right? And the thermal fluctuations is like if this thing was getting blown by wind so that it can't fall over, and then afterwards it falls over. Okay, so it's a pseudo Goldstone boson. So at some lower temperature, this U1 symmetry is explicitly broken. And that means that we can imagine tilting the wine bottle potential. So here we are before. Now at some temperature, the wine bottle potential tilts. So it gets some kind of a bias. And then that means that the potential now has something that depends explicitly on the angle theta. So for example, it could just be the real part of theta. In QCD, particle physics jargon, the thing that does this tilting is something called an instanton or a general non-perturbative effect. But that doesn't matter for us for the cosmology here. The point is something tilts the potential. So what are the action and what's the action in the equations of motion? So before spontaneous symmetry breaking, the action is this, d4x square root minus g, action of the complex scalar field. So Lagrangian of the complex scalar field inside this integral. And the equation of motion that you get from this action, you just do Euler-Lagrange equations, box phi minus d phi minus dv equals 0. And that is solved if we set the radial field to its vacuum expectation value and the derivatives to 0. If we do that, we put it on its VEV, then we end up with post-spontaneous symmetry breaking, an action that only depends on the derivatives of the field theta. And you see now that this action here that only depends on derivatives of theta explicitly has the shift symmetry that I said. So if I send my field from theta to theta plus alpha, where alpha is a constant, this doesn't care about that factor alpha. And it's inherited that symmetry from the fact that this action here of phi is invariant under a complex rotation of phi. So the U1 or shift symmetry tells us that there's no potential. So this potential here did not depend on the angle. So the field theta is massless. This is just doing the maths of what I said in words on the last couple of slides. The non-perturbative effects correspond to introducing an explicit potential for the field theta. Okay, I've canonically normalized it here. That just means the theta has no mass dimension. Theta is dimensionless. It appears in a phase of a complex number. But I can make a canonically normalized field with mass dimension 1 by taking the v inside. The non-perturbative effect just means at some point I write down an explicit potential that depends on this field phi. The potential is m squared f squared 1 minus cosine phi over f, which is just the real part of phi. So I've just biased the potential along one particular direction. I write down plus real part of complex phi. That's this. And then if you want to know what the mass of the field little phi is, you just Taylor expand this potential. This potential has a minimum at phi equals 0. I've chosen that it has a minimum at v equals 0 and phi equals 0. Then you expand around the minimum, and this is just m squared phi squared because the two factors of f cancel out. Right. Okay. Yeah. So here I've just fixed d mu rho to be 0 and assumed that the radial field is massive. So rho is the radial direction. And the mass of the radial direction. Where's that? Here's this. So the mass of the radial mode is of order like lambda v squared. As long as the mass of the radial mode is large, then d mu rho will be approximately 0. In tomorrow's lecture, we will relax the assumption that d mu rho is 0. But for the purposes here, we're just fixing it onto its vacuum expectation value. To use the particle physics jargon, I'm integrating out rho. But it's not strictly necessary. Yes. The cosine. Right. Yeah. So good question. Well, first of all, it's so the potential has to be symmetric under phi under theta goes to theta plus 2 pi, and that's the consequence of it being a complex number. It's the phase of a complex number. So I mean, the fancy way to say there should be, it's like the topology of the field space. So it has to be symmetric under theta goes to theta plus 2 pi, and I've fixed it to be minimized at 0, 0 for phi and 0 for v. So 1 minus cosine is the simplest thing I could choose. But it also comes as I sort of hinted at, if you send v to v plus the real part of complex number phi, okay, with some appropriate constant to take account of the units. So if you do that, if you just tilt the potential a tiny bit along the real axis, the real part of the complex field is the cosine of the angle of that field. So it's also like a linear bias of the potential. And then so these are all nice ways to motivate it. In the QCD jargon, this also arises in what's called the dilute instant on gas. But there are simple ways to motivate it as well. Right, so now we've got an action for the field phi, the axion-like particle, and we can work out what the equation of motion for that is. And it's box phi minus m squared phi plus lambda phi cubed plus ... equals 0. So now the game is just specify the initial conditions, work out what box is, and for the cosmological metric, and solve. Okay, so that's because I could, I've Taylor expanded the cosine potential. This is non-renormalizable. It's a non-renormalizable potential. Yeah, no, but the full cosine potential is non-renormalizable. Because it doesn't arise in perturbation theory. And things that don't arise in perturbation theory don't have to be only up to phi to the 4 perturbatively renormalizable. I'm not a real QFT expert, but I think that's the right way to express it. This isn't a perturbative potential, so it doesn't have to be renormalizable. Okay, so now we just need to compute. So all we're going to do for the whole rest of this lecture is basically think about computing box and solving this equation of motion. So you can compute box for homogeneous FRW, for perturbed FRW. We're going to compute box on the Kerr space-time, and then we're going to solve the equation.
Can I ask a question?
Yeah.
Yeah, so when you add this cos phi term, so you actually would have n degenerate minima here, no?
Right, yeah, very good point, which I've mentioned here. And I was sort of brushing over it. So the field phi, the way, if I write it like this, I can have either 1 minimum or 2 or 3 or 4 or n going around the bottom of this potential. So if I only introduce this linear bias by real part of phi, that corresponds to tilting the bottle like this, and there's a single minimum. So it's not really a cosine in phi. You have to remember that the field small phi is really a phase. So if I just do this, it's 1 minimum. However, and this is something we'll see a little bit more in tomorrow's lecture because it's relevant for the QCD axion, I can introduce a potential that is indeed cosine like n phi over f, or really, so really I've introduced this thing f, which is the thing v, which is the radius of the potential divided by n, and then this n would be the number of domains. I've got a picture of a potential like that. I'm not sure whether it's in this lecture or next lecture, but it'll come up next time. Yeah, yeah. So so U1 has been broken down to a Zn. Yeah. You maintain a discrete shift symmetry. The folk theorem is quantum gravity only has discrete symmetries, not continuous global symmetries. Yeah. Yeah. Oh, right. So think about the complex plane. Right. So I've said that phi, the complex field, is equal to v. It's taken its vacuum expectation value, e to the I theta. So the state of the field is v, and then some angle theta. So then, what is the real part of phi? The real part of phi is nothing more than v cosine theta. It's just from the geometry in the complex plane. That make sense? Okay, good. Right, so now we just got to compute box, specify the initial conditions, and solve. And the initial conditions could be to be linear perturbations about FRW. They could be just FRW, sorry, the space-time that we want box for, or it could be Kerr, the Kerr black hole, which we'll meet towards the end if we have time. Right, so now 2 possible cosmic timelines. The first one I'll call scenario A, when spontaneous symmetry breaking happens before or during inflation. In this case, inflation blows up the value of theta to be uniform throughout the entire universe. So the whole point of inflation is it takes a small patch and it makes the universe uniform. So if I have spontaneous symmetry breaking, I have different values of theta sort of everywhere. If you don't understand this right now, we're going to come back to it many, many times, this different values of theta everywhere. So just keep that in mind, but we will come back to it. But inflation comes, gets one patch of the universe, it's very inhomogeneous, makes it very homogeneous. So now we just have one value of theta everywhere. Life is easy. Life is very wonderful and easy when it's like this. Here's a sort of picture for that. So spontaneous symmetry breaking happens. There's some value of some small horizon, value of theta. Inflation blows it up. And then the hot evolution of the universe starts to happen. And theta takes up the whole horizon. And then at late times, the same value of theta is still the whole horizon. Okay, so the co-moving Hubble horizon shrinks, blah, blah, blah. Reheating, I've just said this. And in FRW space-time, okay, we're going to assume that the Hubble scale, h, is much larger than the mass m at some sufficiently early time. As you go back in time, the Hubble scale increases. Hubble has like some maximum value, about 10 to the 14 GeV. I'm interested in very light particles. At some time in the early universe, Hubble will be larger than m. So I'm going to take the initial conditions for my field, and I'll justify the second one shortly, to just be theta equals theta I, this uniform value, and all derivatives of theta equal to 0. Spatial derivatives are 0 because inflation's made it nice and flat for us, and we'll see why the time derivatives are consistent to be 0 shortly. If the ultralight field that you're interested in doesn't come from spontaneous symmetry breaking in this way that I've just described, that happens for axion-like particles, you could always just posit these initial conditions and solve anyway, and things would be the same. Our goal is to compute the relic abundance given some initial conditions, and these ones are particularly easy. Okay, so the equation of motion, which we're going to come back to shortly, in this scenario is phi double dot plus 3h phi dot. This comes from the FRW metric to compute box. I'll come back to it. Plus m squared phi equals 0. What happens? Let me see if I can. Let's see. Can anyone tell me where the hide controls is? Very good. Right. So the initial value of theta, let's just take it to be random. It means that in this scenario, we can't predict the dark matter relic density, the dark matter mass from the relic density, because I've got an additional free parameter. But this is roughly what happens. So the field starts off with some value, theta I. At early times, the Hubble is much larger than m. That's why we're justified to take the time derivatives going to 0, because this damping term is large. This is just a damped harmonic oscillator with a time-dependent damping coefficient. And then when the damping term drops below the value of the mass, this field starts to oscillate, and this is just a cosine with a. So this is a Bessel function, and it's a cosine with a damping envelope. I've got a nice figure of that, but it's not on these slides, unfortunately. I've got to switch over. Okay, and a comment is, if you're interested in something called ISO curvature, in this scenario, constraints on what's called ISO curvature mean that this scenario is inconsistent with an observably large value of the tensor to scalar ratio. If you want to talk more about that, we can talk about it at the end. Okay, so let's look in a bit more detail at this vacuum realignment scenario. What we need to do is solve the almost homogeneous, almost harmonic equation of motion with a displaced value of phi. So here is the FRW metric, ds squared is minus dt squared plus a squared dx squared. The field is uniform, so dx of phi is equal to 0. So box, if you work out what box is for this metric, it's just minus dt squared minus 3h dt. Then the full solution to this equation would require us to compute the Hubble factor from Friedman, including the scalar field energy density in the Friedman equation, plus other matter. But in order to get an analytic solution here, we're going to approximate Hubble to equal 1 over 2t, which holds in a radiation-dominated universe with a constant number of relativistic species. So now phi double dot plus 3 over 2 t phi dot plus m squared phi equals 0. This gives a Bessel function solution, which I'll show explicitly in 2 slides' time, and gives the solution that I just showed. So the relic density, we find the dark matter relic density by noticing that the energy density in this solution, which I'll show shortly, scales like a to the power minus 3. Oscillations in an m squared phi squared potential behave like pressureless matter. We can think of at early times, the pressure in this field looks like W equals -1, looks like a cosmological constant. The energy density isn't changing, phi theta isn't changing. And then when oscillations happen, it's W equals 0. And the relic density, the thing that we're interested in dark matter, omega h squared, which is just the energy density in some convenient units, 3m Planck squared over mh squared. Mh squared is just 100 kilometers per second per megaparsec in EV. And it turns out that the relic density, and I'll give a bit more of this formula on the next slide, scales in this way, m to the power half phi squared. Let's have a look at this in a bit more detail. Why is it called vacuum realignment? It's called vacuum realignment because I mean, some people, I always get mixed up, vacuum realignment, vacuum misalignment. The field starts away from its vacuum. As I've started displaced from the vacuum, I've chosen to be at theta equals 0, and I start displaced from it, and it realigns or misaligns. It is misaligned, or it does realign. Yeah. And that's what the dark matter relic density is for a scalar field. It's oscillations of the classical field. I'll go through the solution in a little more detail now. Yeah. Symmetry broken before inflation. We'll do the other case in the next lecture. No, I said it is inconsistent with an observably large value of the tensor to scalar ratio. So the tensor to scalar ratio specifies the amplitude of gravitational waves in the cosmic microwave background. And in this scenario, that cannot be large, or this would be ruled out by what's called IISER curvature. So if we observe gravitational waves in the cosmic microwave background, this can't be true. I'll show what happens. Okay, so I've said this. Right, so the exact solution that that arises from the equation that I just showed takes this form. Phi of t has a damping that goes like the scale factor, and then it looks like a Bessel function. So indeed, this just carries on for all t with a damping going like t to the power half a to the minus 3 halves. The constants C1 and C2 are set by the initial conditions. But the asymptotic behavior, so at early times, if I take the time to be very small, the field is approximately constant. If I take the time to be very large, then the asymptotic behavior of the Bessel function gives that I have the field goes like phi a to the power minus 3 halves cosine mt. So the field oscillates forever, but it's damped by the expansion of the universe. But if you substitute a simple cosine like this into the energy density of the field, the energy density goes like a to the power minus 3. So I haven't written that explicitly on the slide, so I'll show it here. So the energy density is a half phi dot squared plus a half m squared phi squared plus dot 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 for the other interactions. If you just take this solution, cosine there, and then we have sine squared plus cos squared equals 1. So rho just goes like a to the power minus 3. So although the field is oscillating, the energy density does not. And the energy density scales like this, goes like scale factor to the power minus 3, like matter, which it should do if this is going to be a dark matter candidate. Right, so in this exact solution, it's for t larger than this parameter ti, but the oscillations of the field begin, go back to the, well, I've got the equation of motion here. Go back to the equation of motion. Here's the equation of motion, but this also isn't a very useful form. Here's the equation of motion in the most useful form to set the timescale. We've got the Hubble factor applying as the damping and the mass m. So the approximation is good when m is much larger than h. Whereas when h is much larger than m, the field is approximately constant. So the approximation is good, like, around here. Yeah, t much greater than ti, and ti is like 1 over Hubble at the initial time. After inflation. So the symmetry was broken during inflation, but then the field starts rolling after inflation. Right, so this is what the solution looks like. We've already seen the solution for the field. Then the equation of state of the field is the pressure divided by the energy density. I haven't written down what the pressure is. The pressure is a half phi dot squared minus a half m squared phi squared. So the ratio of the pressure to the energy density oscillates like cosine 2mt. So here it is. Here's the equation of state. It starts off at -1. When the field starts oscillating, the pressure oscillates, and the average equation of state is 0. And then this is the density. The density starts off as a constant, like the cosmological constant, and then starts going down like a to the power minus 3. So a useful approximation for the energy density, which allows you to approximate for the relic density, is that rho at the scale factor when the oscillations begin is approximately the initial value of the energy density, which is just a half m squared phi squared. The transition in the behavior of the energy density happens approximately when 3h is equal to m. So this constant here is something that you could vary and fit for, but 3 turns out to be a reasonably good approximation. And then at early times, a smaller than AOS, the energy density is constant. At late times, it just scales like a to the power minus 3. So the final energy density is just the energy density at AOS scaled like a over AOS cubed. So if you're familiar with thermal dark matter, you can sort of think of AOS as like the freeze out temperature. I mean, it's not because it's not in thermal equilibrium, but it scales like a to the power minus 3 and nothing else happens after this time. So it's sort of like the freeze out temperature in your head. Yes. So yeah, so if you have the cosine potential or just the m squared phi squared potential, you will only ever go like -1 a to the minus 3. If you want to do something more complicated than this, you have to have a more complicated potential. Yeah, if you have a more complicated potential, you can basically do whatever you want with the evolution of the field. But for the simple ultralight Axion dark matter cosine potential, it's always like this. You can have a slight modification to this behavior if you're up high on the cosine, but we're not going to consider that. So if you take this approximation, you can work out a useful sort of approximate formula for the relic density, which is like this. I'm not going to stay on it. You can find it in the review. So using, yeah. Before the TI when it starts, but so I want it to be way before matter radiation equality that I start this evolution. I mean, if you like, you can take it to be reheating, right? The initial time is like reheating, but the time when it starts oscillating has to be way before matter radiation equality. Because I want this field to be dark matter. So it's a very good point, and we'll come back to that in constraints. I want the time when it starts to oscillate to be way before matter radiation equality, so that it's safely behaving like matter at matter radiation equality. Yep. If you reduce the mass, the oscillations happen later. Yeah. So because Hubble is always going down, and the oscillations start when the mass is equal to Hubble. If I reduce the mass, the oscillations happen later. Very good point. And we're going to use that to set limits on the particle mass as we go on. Right, so if this field is stable, I have to make sure that it does not dominate the energy density until matter radiation equality. And that means that I have to, here, I can work out what the energy density is today in terms of my two parameters, which is the initial field value, which I'm measuring in GeV, and the mass, which I'm measuring in EV. If the initial field value is too large, so if I have some mass, if the initial field value is too large, I'll get too much dark energy, too much dark matter density. I'll dominate the energy density before matter radiation equality. It's ruled out. Equally, as he just said, if I fix the initial field value, if the mass becomes too large, then I will dominate the energy density too soon, and I will spoil all the predictions of cosmology. This gives us the sort of parameter space of this ultralight dark matter. Roughly for this range of masses that we're going to focus on in this lecture, 10 to the minus 24 and a little bit below, up to say 10 to the minus 12, I get the right relic density of dark matter along this line here, too much above it, too little below it. And the initial field values are in the range around 10 to the 17, 10 to the 15 GeV, somewhere close to the grander unified scale, which is about 10 to 16 GeV. Sort of why this model is like suggestive that it might be able to be embedded in some high energy model. I'll skip that. Yeah. Yep. Yeah, we're going to come to them. Yeah, you do. I mean, you want to grow dark matter structure, you have to introduce the spatial fluctuations. You do it. I won't do it in a lot of detail, but you do it in linear cosmological perturbation theory. So you've just had the last two lectures with Shiv on cosmological perturbation theory. Yeah, you have to do cosmological perturbation theory on this field, introduce the perturbations to the metric, perturb box, solve the linear perturbations. Yeah, you absolutely definitely have to do that. I'm not going to do it in detail in these lectures because you've had cosmological perturbation theory. I don't want to go through the gory details again. Absolutely. This slide is about this scenario where spontaneous symmetry breaking happens after inflation. In this case, the field evolution is very messy. You get what's called topological defects. We're going to talk about this a lot in the next lecture, so I'll skip it for now. Right. So yeah, you asked about fluctuations in the field. Exactly. Now we're going to start talking about fluctuations in this scalar field and the formation of cosmic structures. And I'm just about on time. I've got through the first third of my lecture in 30 minutes. So let's hope we're going to stay on track. Right. So I'm going to try and do at various stages in this lecture intuitive ways to estimate the constraints that I'm going to show you. I'm going to show you constraints mostly from my own work, and they're mostly derived by doing a lot of numerical work, solving codes, doing Markov chain Monte Carlos, fitting to data. But I want to try and give you ways to estimate those limits, so you've got a physical feeling for where they come from. So we're going to start doing that now. Estimating bounds, part one. ultralight bosons go from behaving like a cosmological constant to dark matter when the field begins to oscillate. This happens when H is of order M. Okay, so here is a figure that shows us what, so like, you'll want to go away and look at this figure in the paper to really take in everything that's going on in it. But what I'm showing here is the value of the Hubble parameter in red and the size of the co-moving Hubble radius in blue as a function of scale factor, and equivalently as a function of temperature. So by thinking about what these parameters are doing, we can get a sense for what's going on, right? When do we know for certain when dark matter was around? We can read off H at this time and get a constraint. I say, okay, I know for sure dark matter should be behaving like dark matter now. So the mass had better be larger than Hubble now. What's Hubble now? 10 to the minus 33 eV. Mass would absolutely definitely better be larger than 10 to the minus 33 eV, or it's not behaving like 8 to the power minus 3, behaving like matter. You go, okay, I absolutely definitely have to be behaving like dark matter at the CMB. Here's the CMB. CMB is temperatures just below 1 electron volt, and a scale factor of about 10 to the minus 3, redshift 1100. What's the Hubble factor there? Hubble factor there is about 10 to the minus 28 electron volts. The mass should damn well better be larger than 10 to the minus 28 electron volts if I'm going to be a significant fraction of the dark matter. We go back in time. We say, I know that I'm absolutely definitely behaving like dark matter when the co-moving Hubble radius was 1 megaparsec. Co-moving Hubble radius 1 megaparsec corresponds to scales corresponding to galaxies, the Milky Way, things like that. I absolutely know that dark matter was around when the size of the horizon was about 1 megaparsec, when things like galaxies were forming. Okay, so then when the size of the horizon was 1 megaparsec, the temperature was about 100 eV, scale factor was 10 to the minus 6, Hubble was 10 to the minus 23 and a bit. Should probably be heavier than that. Once we go further back in time into smaller co-moving Hubble radiuses, then all of the rest of this involves nonlinear structure formation. And it gets more complicated to set limits from structure formation. But we've just worked out 3 sort of limits of increasingly more powerful on the mass of the dominant component of dark matter. Heavier than 10 to the minus 33 eV, absolutely definitely. If all you know is the CMB, heavier than 10 to the minus 28 eV. If all you know is structures on scales of a megaparsec, heavier than about 10 to the minus 23 or 4 eV. Everything else, nonlinear structure formation. Okay, so that's what. So I'm just saying that now. So a very useful thing to remember as a sort of particle cosmologist is what is the value of H naught. Well, H naught is 100 kilometers per second per megaparsec. That means that every megaparsec you move away from me, the Hubble flow means that you have a velocity of 100 kilometers per second. That's why we write it in these funny units. But okay, of course, kilometers and inverse megaparsecs cancel. This is something with units inverse seconds. This inverse seconds I can convert to EV. This is 2.13 times 10 to the minus 33 EV times little h. Little h is about 0.7. This is about 10 to the minus 33 electron volts. Very useful number to remember. Okay, so this is what I've said. Demanding that dark matter is dark matter today gives us mass larger than 10 to the minus 33 eV. Demanding that dark matter is dark matter at matter radiation equality tells me that the mass is larger than 10 to the minus 28 eV, and so on. Now we're going to move beyond just, yeah. Right, so I'll just go through that again as a bud. So the field phi, or rather, let's say, yeah, so the field phi starts with some value and starts to oscillate. The field starts to oscillate when the Hubble parameter is of order the mass of the particle. That's because the equation of motion is a damped harmonic oscillator where the Hubble parameter is the friction. when the field starts to oscillate, the energy density of the field goes from being constant to going like a to the power minus 3. That happens when, okay, 3h is of order m. And if I want my field to be behaving like matter, it better be after this time. Anywhere, anytime, any period of the universe when I know that dark matter, and I'm assuming that this field is some significant fraction of the dark matter. I know that dark matter is around, it's behaving like dark matter, I'd better be at times later than this. Okay. Good. Yeah, and here I'm just writing down Hubble in some useful way. All right, good. Perturbations. As was mentioned, have to introduce perturbations into the field. I have to then write down the metric in, in perturbed coordinates in synchronous gauge or Newtonian gauge or whatever. I have to work out the equations of motion. I'm not going to do cosmological perturbation theory with you. If you write down the Klein-Gordon equation and you perturb it and you do some changes to variables and so on, you end up with an equation of motion that looks like this. I'm not going to derive it. You can read about it in the reviews that I cited. This is the dark matter over density, delta rho over rho for dark matter in this field phi. It turns out to look like this: delta double dot plus 2h delta dot plus k squared c squared over a squared minus 4 pi g rho delta equals 0. You actually saw this equation already in one of the lectures today. What does this equation look like? This looks like the Jeans equation with a pressure term and a gravity term. So the gravity term wants to make overdensities grow. The pressure was 0. Then the overdensities would grow like A, the scale factor. This is linear growth of matter fluctuations, which you probably saw in the lecture on cosmological perturbation theory. But now there's a pressure term, and the pressure term arises from perturbing the Klein-Gordon equation. So if I perturb the Klein-Gordon equation, I have an equation that looks like, now I introduced the gradients, right? A phi double dot minus grad squared phi minus m squared phi, and then I'm just going to say equals some source term that depends on the gravitational potential and the field phi itself. I'm not going to bother writing that down. But this equation now, oh yeah, still the Hubble friction. You can see that this equation here now has a gradient term. And so that is where this k squared is coming from in this equation of motion here. You have to do a few changes of variables and so on, but that's where it's coming from. K being Fourier conjugate to distance. So you can see that this equation, if the term on the right-hand side of the bracket is larger than the one on the left-hand side, it will have a growing solution. This is a damped harmonic oscillator with a scale-dependent mass. But if the term in the left-hand side of the brackets is larger than the right-hand side, this would have an oscillating solution. The scale at which these two terms are equal is called the Jeans scale, after this man, Jeans. So c squared equals k squared over 4m squared a squared. So the effective sound speed here also depends on k. So this is where the k comes from in the L. That's where the k comes from here. This k is a bit different. Okay, so this is an effective sound speed. There is a Jeans scale where these two terms are equal, and it looks like this. If you plug in the numbers, the Jeans scale at matter radiation equality turns out to be what's relevant for structure formation, is 9 inverse megaparsecs times the particle mass divided by 10 to the minus 22 eV to the power half. If I increase the particle mass, the Jeans scale goes up. Okay, so for all k smaller than the Jeans scale, perturbations grow. All k larger than the Jeans scale, perturbations oscillate and don't grow. So the Jeans scale separates where this thing behaves like cold dark matter, perturbations grow, from this thing has oscillating perturbations, does not look like cold dark matter. So for this particular particle mass, 10 to the minus 22 eV, scales k smaller than 9 inverse megaparsecs, length scales larger than 1 over 9 megaparsecs, looks like cold dark matter. Scales k larger than 9 inverse megaparsecs doesn't look like cold dark matter. If I increase the particle mass, that scale and that k goes to larger k. Higher particle mass looks like cold dark matter on increasingly smaller and smaller and smaller scales. I'll remind you that that a WIMP is not actually cold dark matter on all scales. A WIMP has a free streaming scale. Some particular K, it happens to be very, very large, corresponding to halo masses around an Earth mass, below which it does not behave like truly cold dark matter. So even a WIMP isn't cold dark matter. This scalar fields are not truly cold dark matter. If you make the mass large enough, they look like cold dark matter. This suppression starts at 9 inverse megaparsecs, physical length scale 0.1 megaparsec. Right, so I want to give you a little bit of intuition for the gene scale. So let's consider an observer moving with the Hubble flow. I'm sitting here, and there's an observer, and the observer is moving away from me with the Hubble flow. So here's Hubble, and Hubble is our observer, and he's moving away from some density of axion dark matter on the Hubble flow. Initially, their separation is small, and V is equal to HR. Because V is small, because R is small, the de Broglie wavelength, which is 1 over mv, is large, and their separation is initially larger than the de Broglie wavelength. If I got this inequality the right way around. Yeah, okay. V is small, de Broglie wavelength is large, R is less than lambda de Broglie. Sorry. We can't localize the axion unless the separation is larger than lambda de Broglie. At early times, lambda de Broglie is large because V is small. Me and Hubble and the axion are in the same de Broglie wavelength. There you go. They're in the same de Broglie wavelength. Oh, the animation didn't work. There's meant to be an animation that makes this get bigger. Okay, then you imagine that because Hubble is on the Hubble flow, he moves further away from the lump of axion dark matter. His velocity goes up. As his velocity goes up, his de Broglie wavelength goes, the de Broglie wavelength of the axion goes down, and at some point their separation will be larger than the de Broglie wavelength. And then you can start to localize the fluctuations, and he'll start to be able to see structure formation happening of the axion. Sorry, the animation didn't work. I think I didn't put the right slides in. Okay, so we've got everything we need to start thinking about constraints on ultralight axions from cosmological observables now. So let's work out what they are. We have the equation of state W, which is the homogeneous pressure. It appears in the Friedmann equation, and it affects the expansion rate. We have the sound speed, CS, which is related to pressure perturbations, and it affects the growth of structure. This is the standard components of cosmology. Equation of state 0 for CDM and baryons, and 1/3 photons, -1 for the cosmological constant. Equation of state sound speed 0 for CDM. For baryons, it goes from 0 to 1/3, and depending on how strongly coupled they are to photons. And for photons, it's 1/3. Lambda, the sound speed is irrelevant. It doesn't cluster. It doesn't have any perturbations in it. Ultralight axions, ultralight bosonic dark matter, do not behave like either pure CDM or like baryons or like photons or like lambda. They have an equation state -1 at early times, 0 at late times. Sound speed, effective sound speed -1 at early times, they don't cluster. And this C effective that I wrote down a couple of slides ago at late times. What the cosmologists do, we measure 2-point functions on the sky, normally in Fourier space. So a 2-point function of the temperature fluctuations, a 2-point function of the galaxy number counts, a 2-point function of the lensing potential. It's not really -1. If you plug -1 into a standard fluid, I've written that so that it looks a bit complicated. There's a frame in which you can interpret it as being -1, such that means that fluctuations don't grow. There's a fluid frame where if you put C equals -1, all the time derivatives vanish. Really, I just mean it doesn't cluster. The sound speed is 1 in the co-moving frame, It's the co-moving frame where the instabilities matter, and the sound speed's 1 in the co-moving frame. It's -1 in the Newtonian gauge. Right, so we observe the 2-point functions on the sky. Then we compare the 2 theory predictions for these 2-point functions. And then we do some Bayesian parameter fitting with some Markov chain Monte Carlo, and we work out what the constraints of the parameters are. CMB, for example, measures the expansion rate via the Sachs-Wolf effect at late times, or via the damping scale at early times. We'll look into this a little bit more. So it's going to be sensitive to the equations of state of these parameters, of these components. Late time observables, things like the galaxy power spectrum, are sensitive to the expansion rate and to the growth of structure. So the galaxy power spectrum is going to tell us, probe things like the sound speed. Let's have a think about the scales of interest. We've actually already looked at that, but let's look at them again. No, I'm going to skip through this because I've already shown you what Hubble was at different scales. Let's skip that. CMB power spectrum. This is what the CMB power spectrum looks like. This thing DL is LL plus 1 CL over 2 pi. CL is the spherical harmonic transform of the 2-point correlation function of the temperature. And this is what the CMB looks like. On large angular scales, the large angular scales probe the distance to the CMB, and they're sensitive to dark energy, to the equation of state at late times, this bit here. The small angle CMB, large multipoles, the acoustic peaks damp away. This is caused by diffusion damping, and the diffusion damping scale is given by some integral of the Thomson scattering rate that depends on the scale factor. So it's sensitive to the evolution of the scale factor during this epoch, during the epoch prior to recombination. So it probes the equation of state of matter at early times. So let's have a look at the CMB constraints on ultralight dark matter. We can estimate them. Consistency with lambda CDM expansion rate up to around a redshift of 10 to the 5. If you know that, you know that it's consistent with the lambda CDM expansion rate at redshift 10 to the 5. I actually took this number from one of your papers, Superradiance. And then we could say, okay, dark matter before, if dark matter had to have formed before redshift 10 to the 5, you go and look up what h of 10 to the 5 is. You get roughly this value for the mass on that chart that I showed you before. You go h of 10 to the 5, h of redshift 10 to the 5, mass greater than 2 times 10 to the minus 25 eV. To do this in a precision way, you have to solve the Boltzmann equations for that perturbed scalar field coupled to everything else in the universe. You do a Markov chain Monte Carlo with 6 standard parameters plus 2 more parameters, one for the mass of this particle and one for its energy density. And you can do that using a code called Cosmosis, which handles the likelihood of the CMB in the Markov chain Monte Carlo, and a code called Axion CAM that solves the Boltzmann equation for you. And this is what results from such an analysis look like. Here's the CMB power spectrum. And here I'm taking the dark matter to be all composed of ultralight axions, and I'm changing the mass. So if I have a mass of about 10 to the minus 26 eV, blue, you can just about see that it's different from lambda CDM, and quite different there. So 10 to the minus 26 eV excluded, and make the mass much smaller again, down to about, say, 10 to the minus 27 EV. Here, 10 to the minus 27 EV is very obviously different from lambda CDM. So if I kept all of the parameters fixed, you could see just by looking at this that the mass would have to be larger than 10 to the minus 27 EV. And this is because the transition in the equation of state from -1 to 0 is happening on scales that are probed by the diffusion damping here. So if your mass is too small, the transition of equation of state from -1 to 0 happens on horizon scales that are probed by the diffusion damping of the CMB, and it changes the heights of the acoustic peaks. And this is just coming from the effect on the background expansion being different from lambda CDM. Yes. So this, so here I'm showing it being all of the dark matter, just for illustration. I'm going to show you the results if I vary the fraction shortly. No, so here I'm fixing the particle to be all of the dark matter. So it would be for some particular initial amplitude that puts you there. I did have a plot where I show the constraints in terms of initial amplitude. It was quite a while back, but I can show you it another time. If I look at the opposite regime, if I reduce the mass below 10 to the minus 27 eV, then I start changing, which is the Hubble scale where, at the when the CMB was formed. If the mass is much smaller than 10 to the minus 27 eV, I start to like change the distance to the CMB, I start to change the ISW, and you really can't be very much of the energy density. So now I can make a plot of log of the particle mass versus energy density omega AH squared, where 0.12 here is the dark matter relic density. And these are now points from a Markov chain Monte Carlo in different mass bins. And let's have a look at what's going on. So first of all, let's start at 10 to the minus 24 eV. 10 to the minus 24 eV, and I've colored the points by how much cold dark matter there is. So I've got a mix of cold dark matter and this component, because I want to say how much am I allowed of this component. If I take 10 to the minus 24 eV and I make it all of the dark matter, omega AH squared about 0.12, then omega CH squared goes down to 0. I have to keep the right amount of dark matter total. And similarly, 10 to the minus 25 eV, the CMB can't really tell the difference between 10 to the minus 25 eV and cold dark matter and go all the way up. However, as soon as you drop much below 10 to the minus 25 eV, you start to mess with the diffusion damping scale of the CMB, and you're suddenly restricted to be a small fraction of the dark matter. This behavior continues all the way down to 10 to the minus 33 eV, when you can start to have a large energy density. But notice that you have a large energy density, but omega CH squared remains around 0.12. At 10 to the minus 33 eV, I can have a large energy density by making omega lambda go down. So anything less than about 10 to the minus 33 eV looks like dark energy. Right, so I can now put those constraints on a different type of plot. So I've got cosmic energy density, omega versus mass, and this region here in gray is excluded by the CMB. So this is so you've got the dark matter density. Oh, sorry, that label should be up. You've got the dark matter density here. So everything has to be below the dark matter density unless you're very light, when you can go up to dark energy density. You can read this plot like you read constraints on primordial black holes. You have some constraints on the fraction that they're allowed to be at different masses. And Planck excludes this big region here. If you look to the future with next generation CMB, CMBS4, you can get some exclusion. In terms of field value, if I fixed the field value to be the gut scale, I would predict to be living in this gold region here. So you see that the current limits on the fraction don't reach the sensitivity to probe the gut scale. Right. In the interest of time, I'm going to skip talking about birefringence, but yeah. But if you fix it to the gut scale, then you get the right amount of dark matter in the range about 10 to the minus 21 to 10 to the minus 16 eV, and too much dark matter anywhere heavier than that. But if for the light ones, Planck is not sensitive to it being the gut scale. It would have to have larger field values in the gut scale to be excluded by Planck. Right, I'm going to skip birefringence in the interest of time. I'm just going to mention very briefly how you go beyond the CMB. You go beyond the CMB by considering late time observables like the matter power spectrum. So on here, you have CMB constraints on the matter power spectrum marked in blue from Planck, and they extend to about here. They go from large scales to about K of 0.1 inverse megaparsec. CMB probes large scales. Large scales correspond to small particle masses. CMB is only sensitive to those particle masses up to about 10 to the minus 25 eV, which isn't very large at all. If we want to get stronger constraints on the particle mass, we have to consider galaxy observables. So here we've got the BOSS DR9 Lyman alpha forest and the DES Y1 cosmic shear. And galaxies probe the matter power spectrum down to up to larger wave numbers. If you remember the gene scale, larger wave numbers corresponds to probing larger particle masses. I'm not going to have time to go in any detail into discussing constraints in the matter power spectrum, but consistency with CDM, the black line here is CDM. So if you want to be consistent with, it's consistent with cold dark matter, so that means that on all observed scales, the effective sound speed has to be 0. The equation of state has to be 0 on scales that are when these modes entered the horizon. Just very quickly, what does the power spectrum look like in this model with a gene scale? It looks like this in a sort of cartoon. CDM, well, not quite a cartoon, sort of a cartoon. It's a real computation. CDM looks like this. If I have this gene scale for dark matter, the power spectrum looks like this due to these wave-like gene scale effects that appear on small scales or large wave numbers. Galactic halos correspond to these scales in the power spectrum, so I better look like CDM on scales corresponding to galactic halos, but I can depart from CDM on scales corresponding to, say, dwarves or smaller. We can estimate those scales. I already talked about that with setting the size of the horizon to be some particular value and reading off the value of the mass. I'm just going to skip through the cosmology constraints to get to the next part. But just to flash up an example of how you can do these power spectrum constraints, you can read about it in this paper that we wrote in 2021, constraints from the dark energy survey, weak lensing shear correlation function. That's those gold data points that I showed on the power spectrum before. That's a bit of a cartoon. This is what really happens. There's some 2-point correlation function, and there's some nonlinear matter power spectrum, some convergence power spectrum, and the colored lines here for different values of the particle mass. And for some particular value of the particle mass, you don't fit these data very well anymore, and you place a limit. And from the DES Y1 cosmic shear in a Bayesian analysis, marginalizing over all the nuisance parameters, you discover that the mass of the particle has to be larger than about 10 to the minus 23 eV if it's going to be all the dark matter. We haven't done the constraints varying the fraction in this cosmology yet, because we lack the theory tools to do it. But we forecast that DES Y3 will be able to increase the limit by about an order of magnitude, and that Euclid, using the same observables, will increase the limit by another 2 orders of magnitude again. The advantage of using lensing here is it's a direct probe of the dark matter density. You can also do a constraint with the Lyman alpha forest. You can read about it here by Rogers and Peris, and Lyman alpha forest gives you a very strong limit on the mass, larger than about 2 times 10 to the minus 20 eV. That's all I want to say about cosmological constraints. And now I'm going to go to talking about more compact structures inside galaxies, and we're going to talk about solitons and black hole superradiance, hopefully all of it in 20 minutes. Okay, so if we want to look more at constraints on ultralight dark matter, we need to go to smaller scales. We need to go inside galaxies. The physics changes a bit inside galaxies, so that's why we're going to spend a bit of time on it. The inside galaxies and at late times, everything is non-relativistic. So rather than working with the Klein-Gordon equation that's written on the board, we're going to take the non-relativistic limit of the Klein-Gordon equation. We take the non-relativistic limit in this way, which is a WKB approximation. I write my real field phi as being equal to some complex amplitude field psi times e to the IMT plus its complex conjugate. Then I plug this approximation into the Klein-Gordon equation. And I can also write the complex field psi in radial coordinates if I want. If I plug this approximation into the Klein-Gordon equation and take the non-relativistic limit, it reduces to a Schrodinger-like equation. It goes from being second order to being in time to being first order in time, non-relativistic, right? Something that's non-relativistic has to involve a different number of time derivatives and space derivatives. So I go from a Klein-Gordon-like equation to a Schrodinger-like equation with 1 time derivative and 2 space derivatives. It's a non-linear and Schrodinger equation, because the gravitational potential itself is sourced by the field. So here I'm ignoring anything else like baryons or gas, well, like baryons, which is gas, that could appear on the right-hand side here. But in principle, that's easy to put in. So, and this is another way of seeing the emergence of that gene scale, is that the gradient energy in the Schrodinger equation, which is coming from the gradient energy in the Klein-Gordon equation, acts to push out any fluctuations, any density perturbations, small density perturbations in psi. People call this the quantum pressure. It's not quantum, it's not a pressure, but never mind. This is a equation of motion for a classical condensate. This is not a quantum equation. And this is what gives rise to that effective sound speed. It's non-linear and it's non-local because of the Poisson equation here. So it's a difficult equation to solve. And this gives rise to everything, all of the really fancy fuzzy dark matter physics, gives rise to stable solutions, Axion stars, solitons that we'll try and talk about. It gives rise to waves and interference. And it's fundamentally different from most other dark matter models on small scales. Fundamentally different from cold dark matter, which doesn't have this term. Fundamentally different from warm dark matter, which is modeled by a Boltzmann equation with velocity dispersions. Okay, so the challenge is to simulate this equation over a wide range of scales. Here's a snapshot from a simulation of this equation by Philip Marsh, which shows a galactic filament. And in this galactic filament, there's a halo at the node. Inside the halo, there's an Axion star. And along the filament, there are interference fringes. It's on a 0.25 megapascals. A bunch of other people know how to solve this equation numerically. And here are some snapshots. And here's a really nice one that has both a mix of cold dark matter and fuzzy dark matter. And people have also done mixed, FDM, mixed fuzzy dark matter and gas. So you can see here along the filaments, the distribution of gas, as well as the distribution of dark matter. So people can solve this numerically, but what can we learn about it analytically? Well, first of all, what does it look like inside a halo? So inside a halo, this is a movie from a simulation by Jan Veltmath. So this is this is inside a halo made of this scalar field. Here's the compact soliton in the middle that we'll talk about in a few slides' time. But this is what it does dynamically. So it's not static. So the soliton stays pretty coherent and blobs around. In the outskirts of the halo, there's this sort of turbulent field that's moving, that has a well-defined sort of correlation length and changes on a characteristic time scale. So it's got a characteristic length and a characteristic time scale over which the dark matter is evolving in a coherent way. And this does not happen in cold dark matter. The average profile of this field outside the soliton looks just like cold dark matter. If I average over angles, then averaged over angles, there's no time variation anymore. And the radial profile looks like an NFW profile. However, it's got this coherence length and coherence time. I'll do that, right? So the velocity field obeys the Maxwell-Boltzmann equation. No, the simulation starts at redshift 1000 with linear perturbations. The simulation starts with perturbations drawn from that linear power spectrum that we can compute in perturbation theory, and then evolves forward, solving the Schrodinger equation. Yeah, they form. They form rapidly due to there's initial coherence in the field, which comes from that sound speed term. So the field has some initial coherence, even at very high redshifts. And as soon as nonlinear structure formation happens, as soon as like gravity becomes important, the solitons clump together out of the initial coherence. Right, so there's a coherence length and coherence time. The coherence length is roughly the de Broglie wavelength with a factor of 2 pi. The coherence time is roughly the time it would take a perturbation to cross the de Broglie wavelength. So length over v squared, length over v. You can understand the time dependence of this by thinking, okay, I've got the Schrodinger equation. I need to write down the eigenfunctions of the gravitational potential, but the energy density, so I can write down the the wave function as some x dependent part plus some time dependence given by the energy eigenvalues. But the density of dark matter is the square of that wave function, so I get a modulus squared term plus cross terms from different energies. So you take the modulus squared of the wave function, and you have many different energies, and you end up with a time dependence. Right, and then what does that time dependence do? That time dependence leads to a distinct physics from cold dark matter. So the coherent patches, you can think of them as being like quasi-particles. And these quasi-particles will collide with any stars that are present in that mix of dark matter and lead to what's called two-body relaxation. So this is the formula for the two-body relaxation time. It's in chapter 1 of Binney and Tremaine, if you don't know it. And this leads to heating and cooling, two-body relaxation, scattering of a star with these quasi-particles. You get heating of a distribution of stars if the mass of the stars is less than the mass of the perturber, less than the mass of the quasi-particle. And otherwise you get cooling. And this is gone through in detail in one of the problems that I mentioned. So we're just going to talk about it quickly. Let's consider the old star cluster in Eridanus 2. So Eridanus 2 is an ultra-faint dwarf. It has a star cluster in it. And the stars in that, and from the mass of the dark matter halo of Eridanus 2 and its velocity dispersion, we can compute the relaxation time. We can compute the quasi-particle size and the relaxation time of the star cluster. And this is what we know about the star cluster. It's old, it has a particular radius. If the dark matter is too light, then this relaxation time turns out to be too fast. And the star cluster will heat on a timescale that is much, much faster than its age, and therefore it shouldn't be stable. If I make the dark matter heavier, then the quasi-particle mass decreases and there's no longer any heating. And this is what it looks like. So if you imagine this star cluster, this is its half-light radius, RH, as a function of time. If the dark matter is relatively light, 8 times 10 to the minus 21 eV, the half-light radius grows very quickly and becomes much larger than its observed value on timescales much shorter than the age. If I have a mass of, however, about 8 times 10 to the minus 20, about 10 to the minus 19 EV, I can just heat the star cluster to have its radius. So that would just be consistent with the observables, with what's observed. So and this is done in a lot of detail in this paper by Dalal and Kravtsov, and you end up finding out that this star cluster, due to the dynamics of the fuzzy dark matter halo, the existence of this star cluster excludes the dark matter from being lighter than 3 times 10 to the minus 19 EV. And there are many other related bounds due to this relaxation physics. So the mass of the quasi-particles is given by the local dark matter density times the de Broglie wavelength cubed. So you can think of them being like a these coherence patches as acting like a quasi-particle that scatter the stars. So the mass of the quasi-particle depends on the mass of the dark matter particle through the de Broglie wavelength. Yeah. They're all weaker than this limit. So this is the strongest one. Yeah. But once we're like inside galaxies, there's a lot, well, okay, Dalal and Kravtsov did this very carefully, but there's a lot of squiggles going on here. You might want to, you might make some arguments about the formation of the star cluster. Once you're inside galaxies, like things are less robust. I mean, I think this is a robust limit, but there might be ways to argue your way out of it, but you can't argue your way out of a constraint from the CMB, which is linear physics, like super robust. Yeah, this is the most powerful limit on the particle mass. Yeah, so if you put this mass into the matter power spectrum, the matter power spectrum would look like CDM to very small scales. Okay, right. I'm a bit behind on my time. I've only got 10 minutes left to do a half-hour section, so I'm just going to like show you a few bits of this. I'm sure I'll put my slides online and you can look at them at your leisure. Solitons. So I've talked about Axion stars in my talk on Monday. I'm going to show you them here in the non-relativistic limit. There's a sort of problem on them. Well, so the solitons are ground state solutions of the Schrodinger-Poisson equations that I've written down already, that are one parameter family. So we take the ansatz that the wave function is just a radial dependence and some energy eigenvalue. I then write down the Schrodinger-Poisson equations, and they look like this. And then I look for a solution of these equations. And you can solve them using a shooting method. So it's a boundary value problem with some eigenvalue gamma. So we fix the field chi to have some constant value at r equals 0 to decay at r equals infinity, such that it has a finite, so it can be integrated to a finite value from r equals 0 to infinity. And you solve this boundary value eigenvalue problem. You have to solve it numerically, but you find the following eigenvalues. And the solution looks like this. So here's chi of r, I've normalized it to 1 at the origin, and it decays like this. So the wave function oscillates, but the density which is the square of the wave function, is a constant because it's just got one energy state in it, and this is the soliton solution. So in the non-relativistic limit, it's a true soliton. It's time independent. It's localized, and that's because in the non-relativistic limit, there's an effective U1 symmetry for this thing psi. If you look at this in relativistic theory, the field phi, which is this times e to the imt plus its complex conjugate, the field phi actually oscillates, and the relativistic limit, the density itself also oscillates. No, the density doesn't, but the metric oscillates. So it's not a soliton, but it's an oscillating compact solution. I'm going to skip soliton formation, but you can read about it in these papers. I'm going to skip the soliton distribution because I talked about it in my lecture on Monday. And I'm going to spend 10 minutes telling you about superradiance, because I think I've got quite a nice description of it to give you. So I said that all of this lecture is about solving the scalar wave equation given some metric. Find out what box is, solve for what phi does, given box. That's what we're going to do here on the Kerr metric. But first of all, we need a bit of physical intuition for what's going on. So the physical process that you can imagine going on here is something called the Penrose process. So what I'm drawing is the space-time of a Kerr black hole. It has an inner horizon, an outer horizon, and an ergo region. Inside the ergo region, all the frames are co-rotating. So if you go into the ergo region, you have to rotate around the black hole. What happens in the Penrose process is you imagine a particle with positive energy going into the ergo region. It's forced to co-rotate. Then it drops part of itself into the horizon. That part has negative energy and it's lost to us, and it gets kicked out with larger energy than it went in with. Energy conservation demands that this extra energy is taken from the spin of the black hole, so it spins down the black hole. This is a similar process to, like, you have a spinning cylinder and you throw a particle onto it such that it has to rotate, and then it will get thrown off with more angular momentum than it went in with, the classic superradiant process. If you now imagine, as Preston Tucholsky did, surrounding your black hole with a mirror and having particles going around and undergoing the Penrose process, they're a rocket and you're on this particle and you're dropping things. And then this can happen over and over and over. So here's the event horizon, here's the ergosphere, and this happens over and over again, and will eventually extract all the spin energy from the black hole, and it's called the black hole bomb. And so here's a video from Kurzgesagt of this. Let's not watch it, actually, it's quite a long video. Go and watch this video. It explains superradiance. Okay, how does this relate to the Axion field on Kerr? So we'll only relate it to the Axion field on Kerr right at the end. We have to start by computing the box operator on Kerr and solving the equations of motion. So this is the Kerr metric. Okay, it looks horrible, but we can compute box. I'm going to use what are called Boyer-Lindquist coordinates. I'm going to normalize this is Boyer-Lindquist coordinates and in units where Newton's constant is 1. Appearing in here is A, the black hole dimensionless spin, which goes from 0 to 1. Some functions of the parameters, which define the horizons. And then we compute box. So the equation of motion is just box minus d phi v equals 0. To solve this equation of motion, just like we solved the equation of motion in cosmological perturbation theory before and got a Schrodinger equation. So I wrote down phi equals psi e to the imt. I can similarly try and solve this equation in an approximation like this. I have some energy eigenvalue omega and some spheroidal harmonics and some angular quantum numbers. If you make this ansatz, then similarly you can reduce the Klein-Gordon equation into a Schrodinger-like equation in an effective potential. And the radial coordinate here is what's called the Wheeler-Tortoise coordinate. So the effective potential now tells you everything you want to know about this solution. So I'm considering the field evolving in a background with an effective potential. This is what the effective potential looks like as a function of radial coordinate. The ergo region is over here, and the event horizon in these coordinates is at r equals minus infinity. The effective potential has a barrier and a minimum. So bound states can live in the minimum, but they can also tunnel through the barrier. And that's what gives rise to this to this process now. So you can think of the tunneling into the barrier as being like the Penrose process, dropping his extra bit of mass off and then getting boosted up in energy, and the barrier as acting like the mirror in the black hole bomb. So it's a gravitational atom. It has an effective coupling constant, GMM. If this equation has an imaginary eigenvalue, then the solution for psi will grow. And the interpretation of that is Penrose process mirror. And conservation of energy demands you extract spin from the black hole. This isn't, okay, so this is a classical wave equation. So all you ever do is solve this classical wave equation. What it really, okay, if this is a classical wave equation, it means that the classical waves look like this. And the classical waves have some of them on the other side of the barrier. You don't need to think of it in terms of particles and quantum. But you mean you can also, you can also do that. You can write down the, you can think of it as quantum fluctuations if you want to. But what people actually do is solve this classical equation of motion and look for imaginary energy eigenvalues. But you can interpret it the way that I've said. But really, it's just classical equation of motion with imaginary eigenvalues. Does that make sense? Right. Okay. I want to just get to the limits. Okay. So this process happens roughly when the Compton wavelength of the field is resonant with the size of the ergo region of the black hole. That means that it's got some overlap to drop itself off into the horizon, but the wave function isn't too big that it can't fit inside the bound state region. However, when you extract spin from the black hole, the ergo region gets smaller A Kerr black hole approaches a Schwarzschild black hole with no ergo region when you extract spin. When the ergo region gets too small, when the spin gets too small, the particle wavelength is no longer resonant with that region, so the process has to shut off. So you start with no particle. You start with like 0 initial condition for this field, but there's an imaginary eigenvalue. So even a tiny fluctuation will grow exponentially. The tiny fluctuation grows exponentially and extracts spin from the black hole. As you extract spin from the black hole, at some point the ergo region gets too small and the process stops. So you expect that if you have a particle that's resonant with a given black hole, it will spin it down and reduce it to some minimum value of spin. And yeah, so the superradiance stops when the black hole reaches the minimum value of the spin. So what this tells you is, if I have a particle of a certain mass, I shouldn't expect to see black holes that are resonant with that mass that have high spin. I should always expect black holes that are resonant with a given particle mass to have low spin. However, we know of lots of black holes, and you can measure their spins by, for example, X-ray spectroscopy of the accretion disk. So you can use this to place limits on the particle mass. And that's being shown here in this lovely animation done by a former grad student, Matt Stott. So here on the left-hand side, I've got black hole mass and spin. And I've got 4 black holes with measured mass and spin. They've all got masses around 10 solar masses, but see this one in particular, M33X7 at LMCX1. So these are black holes in LMC and in M33, have a measured value of mass and spin, which is relatively high. So the contour shows up to 3 sigma. Now, the colored region that's moving across here is the region that you expect to see no black holes given the superradiant process, or a value of the particle mass, which we're using mu here to not confuse with the angular magnetic quantum number, which is changing, moving to the left. So, and the color tells you the mass. So, if I shouldn't have these black holes, then if this region overlaps the region where I can see black holes, that particle is excluded. That's what I'm showing here. So here's the exclusion probability as a function of mass for the colored lines for the different black holes. It's just the overlap of these 2 regions. So you see that as I change the mass from large values to slightly smaller values, the exclusion probability goes up to 1. Then when I reduce the mass further, the exclusion probability drops to 0. So there's a range of masses, it covers a couple of orders of magnitude, that is excluded by the existence of these black holes. You can do that for all the known, all the black holes that we could find, all the ones that we used. And here I've got sort of 10 solar mass-ish black holes, and they exclude particle masses between about 10 to the minus 11 and 10 to the minus 13 eV. I've then got supermassive black holes, which have more uncertainty on the spin, but they exist. And they've got masses about 10 to the 8 solar masses. And the supermassive black holes that we used in this analysis exclude a range of particle masses between about 10 to the minus 16 and about 10 to the minus 19 eV. 10 to the minus 19 EV overlaps the limit that we got from Eridanus 2 earlier. So now we've got a huge range of constraints. There's a gap in these limits around 10 to the minus 15 EV because we don't know of any intermediate mass, 10 to the 4 solar mass black holes. And we certainly don't know that they're spinning, even if they existed. So there is no constraint around 10 to the minus 15 EV, which is why I said on Monday that this is one of my favorite mass scales. I'm not going to talk about the Bose-Nova because we've reached the end of the time. I'm just going to summarize all of the limits that we've seen throughout this lecture. And here they are. So as a function of the ultralight bosonic dark matter mass, going from 10 to the minus 34 electron volts, all the way down to 10 to the minus 10 electron volts, covering 24 orders of magnitude, here's the cosmic density that's allowed. First of all, on the right, the limits from black hole superradiance don't care that this is dark matter. They start from vacuum fluctuations. So they just block out a range of masses that are not allowed. But there's a gap around 10 to the minus 15 EV. Yes. Yeah. because it's a negative eigenvalue, exponential instability, just quantum fluctuations are enough to get it going. So it doesn't care about the ambient dark matter density. It's a really powerful constraint. Caveat of the Bose-Nova that I skipped over. That excludes two regions. Then going down in mass, we've got this range excluded by the instability of the Eridanus 2 star cluster. Then we've got a range excluded by the Lyman alpha forest, reionization, dark energy survey, matter power spectrum constraints. Pulsar timing arrays, I didn't have a chance to talk about. And the open regions, by the way, are forecasts to the future. And the CMB excludes a range of masses at even lower values. And then the future SKA intensity mapping, which I haven't had a chance to talk about, it's in the backup slides, will increase these limits by many orders of magnitude and cut out a big chunk over here and start to probe the gut scale, future Lyman alpha forest. These limits aren't the most up-to-date ones. There are some new forecasts, some new limits from the BOSS baryon oscillation spectroscopic survey. Updates of this plot you can find on Kia Rogers' GitHub. That's everything. Yeah, questions? The only regions here where you can be all of the dark matter is 10 to the minus 15 EV or above 10 to the minus 11 EV. So that would look like cold dark matter. Everywhere where you're allowed, you would look like cold dark matter. Now, and everywhere you're pretty much limited to be less than about 10% of the dark matter. So you notice that these limits here don't join up. That's just a problem of methodology. We just need to develop some theory methodology to analyze the existing data, and these limits will join up. I'm working on it. You could, maybe relax the Eridanus 2 limits at the low masses where the approximations that went into deriving them might not be quite so valid. You might be able to get around the Lyman alpha forest limits a little bit by changing the evolution of the temperature of the IgM. There is room to try and relax the limits, maybe here, and have a relatively large fraction of 10, 50%, something like that. But it's hard work. But you would have to work hard, or you would have to change some of the assumptions of this model. I've just done m squared, phi squared, one field. If you change the assumptions of the model, if you change the cosmology, if you change the initial perturbations, maybe you can get around this. But in just the simplest realization, yeah, there's a gap at 10 to the minus 15 EV, and otherwise you're 10 to the minus 10 EV and above, which is the realm of the QCD axion and is the subject of tomorrow's lecture. Yes? Yeah, I'll take the student question first. Yeah. Mm-hmm. Yeah. Right. So yeah, very good point, and something I didn't mention. So these this exclusion region that's fixed here, in the mass and spin plane, is fixed assuming that black hole superradiance is the fastest timescale. So actually, we actually compare the superradiance timescale, which you can get from this eigenvalue of this equation of motion, to the estimated accretion timescale of these black holes. So you have to have the so that's what leads to the depth of this limit, is from making sure that superradiance has to be the fastest timescale in the problem. And for the supermassive black holes, I think we compare it to what's called the salpeter time of the black hole. And for these ones, I think it's the accretion time. You'd have to look at the paper for the details. Yeah, right. Right, but as long as the superradiance timescale is the fastest timescale in the problem, then even if the black hole got spin, it would lose it on a rapid timescale. So yeah, and you have to also make an assumption that the superradiance timescale is shorter than the estimated age of the black hole, for example. So yeah, there are important timescale assumptions that go into that, and probably you could do a better model. You could probably model this better than I have. I think that, and there's a lot of other approximations that go into these limits. I'm actually working with a colleague at the moment to try and do like a community consensus set of limits where we use a better approximation to the data on the black holes. And yeah, timescale is a very important thing to address. Yeah. Yeah, so this is just showing the L equals M equals 1 mode. I think in the constraints analysis, they're here, and we use all the modes up to a certain L max. But how, yeah, there is an issue in the analysis of like of that choice as well. Like how many modes do you include, and how do the trajectories evolve? And we made a relatively simple approximation in this paper, and that's also something that should be better addressed in future. But I think we use all modes up to about L equals 4 in this paper. Yeah, very good question. So if you had superradiance in a background with a large occupation number, would it change? I don't know the exact answer to that. I know that Katie Clough and Pedro Ferreira have thought about this. I don't know how conclusive the paper is. The problem is that for a scalar field, you cannot directly simulate the superradiance process. And that's because for, the metric oscillates on the timescale given by the scalar mass. But the superradiant timescale is way larger than that. You can't directly simulate it in numerical GR. The only regime where you can directly simulate superradiance is for vectors. I mean, it happens that for vectors, the metric doesn't oscillate. So there's not 2 timescales, there's only 1. So you can simulate superradiance for vectors, and then you could try and put a background of vectors into your simulation and see what happens. But for the scalar, you can't simulate it, and I don't. But maybe you could try and look at it analytically. But yeah, I don't know. Yeah, is the answer. But certainly you can't simulate it directly, so you'd have to do it analytically. So maybe that's a good problem to think about. Question, yeah. Yeah. So for the Penrose process to happen, which is that you just imagine throwing a rocket ship at a black hole and letting it drop something. Yeah, it has to come in the same direction of the rotation, so that it gets. So if you imagine the rotating cylinder, you have to throw the ball so that it hits the cylinder like at the right angular speed. So yeah, for Penrose process that has to happen. Yeah. No, so for the scalar field case, you don't have to, we're not actually throwing scalar fields in and letting them roll around. That's just like a helpful way to think about it. We're just starting with vacuum fluctuations and looking for negative eigenvalues. So it's just an intuitive way maybe to think about what's going on. But if it's too confusing to think about the ball and the dropping and the mirror, just think of the Schrodinger equation with negative eigenvalues. In this potential has negative eigenvalues. He had his hand up first, and then I'll come to you. Yeah. Okay, so a few things could change with the cosine potential. Great question. If I use the full cosine potential, let's have a look at the constraints and talk about what will change. Okay, well, first of all, the superradiance constraints will change. So here, so the superradiance has an instability if you have the 5 to the 4 term, which is the first term in the expansion of the cosine. And this means that the superradiance constraints don't apply if the 5 to the 4 term is too large, which is equivalent to f being small. So here I'm showing the limits from, here it's the limit from GRO J1655 on the mass as a function of both the mass and the value of f. For the stellar mass black holes, the constraints go away when f drops below about 10 to the 14 GeV. For the supermassive black holes, the constraints go away once f drops below about 10 to the 15 GeV. So superradiance is affected by the assumption of cosine, and it goes away if f is too small. The other constraints that would be limited, you said exactly the relationship between the relic density and the initial field value changes when you introduce a cosine. It's what's called anharmonic corrections. And if you look in my review, there's a formula for those anharmonic corrections, but you can just compute it numerically. It's only an ordinary differential equation. Most of the other limits don't change unless the initial field value is close to pi. If you make the initial field value close to pi in the cosine, that's when the relic density formula changes a lot. But it also changes these limits here. So if the initial field value is on the top of the cosine, then the curvature of the potential is negative. When the curvature of the potential is negative, then the equation of motion is unstable. So the perturbations grow. And what that means is that if I tune the initial field value to be close to pi, the matter power spectrum, instead of being suppressed, is enhanced. So there's a range of scales over which the matter power spectrum is enhanced if you make the initial field value close to pi. And that's what some people call the extreme Axion model, the extreme wave model. And the group in Taiwan, Shive and company, have shown that the Lyman alpha forest limits can be relaxed if you tune the initial field value close to pi. That was one of the things that I mentioned in answer to Subinoy's question. If you change the potential strictly away from m squared phi squared, some of this changes. And if you tune the initial value properly, you can get rid of the Lyman alpha forest limit. Yeah. So if the initial field value is close to pi, the value of f that you need at 10 to the minus 22 EV goes down from about 10 to the 16 GeV to about 10 to the 15 GeV. It doesn't change that much. But the more you tune the value close to pi, the more f comes down. If I'm remembering the results of the Taiwanese group correctly, in order to get rid of the Lyman alpha forest, f goes from about 10 to the 16 to about 10 to the 15. But it's not a huge change. But yeah, it does change, you're right. Yeah, you were next. Yeah, so right, so I've just approximated it here. We could go back to the slide, but it only oscillates right at the beginning, so it's just flat. Then there's a short time where it oscillates, and then it's flat again. And it's flat again because sine squared. Once you're in the regime where the field looks like this, sine squared plus cos squared is 1, and it's flat. It only oscillates at the very beginning when that harmonic approximation doesn't hold. So in like the first 2 or 3 oscillations of the Bessel function. So you can take actually, and I encourage you to try it. Take the explicit Bessel function solution that's given in the problem solutions and plug it into the formula for rho and check how this happens yourself. Yeah. 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 Yeah, so the time dependence, so if you put the a to the minus 3 halves in, then this is sine squared plus cos squared equals 1 times a to the minus 3. The time dependence of the scale factor gives you the a to the minus 3, which gives you this.